KP classes dedicated to excellence.
All right. So in our last class, we basically discussed about various work calculation, where I gave you the expression for work that was W is nothing but the integral of PdV. Okay. Along with this, we also discussed for different processes like isoporic, isobaric, isothermal, and adiabatic process, and just drawing it in a tabular form. Do make this table so that it is easy for your revision purposes. Okay. So for the isoporic process, mainly the volume will be constant, okay, and the work expression is, it will be zero because there is no change in volume. Okay, so you can write it down in such a manner that what particular process means what term to be constant, and what will be the expression for the work. Okay, so for the isobaric process, basically pressure remains constant and the work expression is given by P VB minus VA. That is the final volume minus the initial volume. Okay. Similarly, for the isothermal process, temperature remains constant and the work expression is given by nRT ln VB by VA, or it can also be written in the form of a pressure, that is nRT ln PA by PB. Okay. Similarly, for the adiabatic process, there will be no net change in heat. So Q remains constant, delta Q equals to 0, or Q remains constant. And the work expression is given by, I'm writing it down over here. It is PBVB, that is the final pressure and volume, minus PAVA upon 1 minus gamma. Okay, so these were the expressions that we created, that we generated for various work functions for different processes. Okay, so make this table, and along with this we also discussed about heat capacity, specific heat capacity, and also generated some relation where I told you that how enthalpy is dependent upon the specific heat capacity at constant pressure. Basically, the expression that we found was dH is ncpdt, and similarly, how internal energy depends upon the specific heat capacity at constant volume. The expression that we derived for that part was ncvdt, right? So these things we discussed in our last class. So make this table and then let me know, and then we will begin the class. Okay. Okay, very good. Okay, so to begin the lecture, it was section number 3, I believe. It was, first of all, it was chapter number 4, that is heat energy. And inside which we were discussing about the third section, that was here I'm going to prove that how the heat is a path function. Okay, we already know that the path variables are only two that are means that are in presently in our course. One is the work done and the another one is the heat energy, right? Heat energy. So we have already seen how the work depends upon the path function, how the work is a path function. Now we are going to see how heat is basically a path function. Okay, so the third section will comprise of heat is a path function. Okay, so consider a system. I'm just drawing a PV curve for this. It will be much more easier to understand based upon the diagram. Okay, so consider a system, say at state A, that is the initial state, and it is going to a state B, a final state, by two different processes, by two different paths basically. Okay, so this is path 1 and this is path 2. Okay, So if you calculate the change in internal energy based upon these particular final and initial states, you will find that the change in internal energy will be same whether the system goes from path 1 or path 2, because internal energy is basically a state function. Okay, so you can directly write it down that del u a to b will be nothing but ub minus ua, the final internal energy minus the initial internal energy. Okay, so using this, if you can directly put this equation in the form of the first law of thermodynamics, right? So with the help of the first law, the first law states that del q minus del w gives du, right? So if you consider for path 1, if you consider for path 1, du will be written as same itself, and the value will be ub minus ua. So I'm just writing it, indicating in the form of du, a goes to b. Okay, and you can write the change in heat will be q1, and similarly the work done will be w1. Okay, you can write it for path 1, right? Consider this to be equation 1. Similarly, for part 2 also you can write it down. The first law, based upon the first law of thermodynamics, du a to b, this value of du will be same because it is a state function that we have already know. Okay, and there will be some change in heat q2 minus w2. I'm just representing it that going from state A to state B using part 2, the heat will be required will be Q2. Okay, so I'm just indicating it. We don't know yet that whether it will be equal or same, equal or different. Okay, so we are just indicating it with the term Q2. Okay, so we can directly write it down that path 1 is given by this equation and part 2 is given by equation number 2. Okay, now what we see here that the change in internal energy is same for both these processes, right? For both the equation, the change in internal energy is same. So what we have to do, we just have to equate these two equations. Okay, so on equating them, you will be obtaining equals to q2 minus w2, right? So you can also write this down as q1 minus q2, q1 minus q2 is equal to w1 minus w2, right? Now, in the last class, we have discussed that work is a path function, and it depends upon basically the path taken by the system in order to reach from one state to another. And the work is basically calculated based upon the area under the curve, right? And since the area under these two curves are different, so W1 and W2 will be a different value. Okay, so since W1 and W2 are different values, so their difference will definitely be not equal to 0, right? Since these two terms are different, they have different values associated with them. So their difference will definitely be not equal to 0. And as since it is equal to the difference of the heat from path 1 and path 2, so definitely their difference will also be not equal to 0, right? So we can directly say that q1 minus q2 is not equal to 0, and hence heat is a path function. Clear? Right? I hope everyone has understood how we have derived that heat is a path function, and how you can express it in case if such questions basically are like indirectly asked in your PSUs when you go forward with your PSUs and other different colleges interview purpose. These questions are being asked. You have to know the basic idea that how they are being calculated. Okay, based upon the diagram of P versus V curve, all of these quantities can be easily calculated. Okay, So please note this down. And if you have any query, do let me know in the chat box. Okay, I hope it is clear to everyone. Done? Okay. All right. So with this, the heat topic is almost completed. Now we will be seeing different free energies that we have discussed earlier, like Gibbs free energy and Helmholtz free energy. We have already seen the equations that G equals to H minus Ts and A is equal to U minus Ts. Now, what we are going to do, we are going to see that how this particular Gibbs free energy and Helmholtz free energy are related to the non-mechanical work done. Okay, we have discussed about the non-mechanical work done. It is a part of the total work that we have calculated earlier. Okay, now what we are going to do, we are going to find out the equation based upon this Gibbs free energy in terms of the non-mechanical work done. Okay, so you can write it down as a new section, section number 4, where we will be dealing with free energy. Okay, it is quite simpler topic and you can easily understand. Okay, so first of all, we'll be studying about Gibbs free energy. You can write down the definition. It is the maximum non-mechanical work. It is the maximum non-mechanical work that can be extracted. It is the maximum non-mechanical work that can be extracted out of the system, at constant temperature and pressure. Okay, it is the maximum non-mechanical work. It is the maximum non-mechanical work that can be extracted out of the system at constant temperature and pressure. Okay, Gibbs free energy, basically it is a maximum amount of non-mechanical work that can be extracted from the system at constant temperature and pressure. Please note down that this is particular and important terminology that is used in this definition, that it remains at constant temperature and constant pressure. Okay, all right, so now we will be seeing how this Gibbs free energy is related to the non-mechanical work. Okay, before that, we have already seen that the total work done is basically the mechanical work plus non-mechanical work plus the loss, right? So this here represents the mechanical work. Del W dash is where I am representing the non-mechanical work. And del W loss is basically the loss of work. Okay, and it is mainly because of the frictional forces. So these are the frictional losses. Okay, all right. So based upon the first law of thermodynamics, we know that del Q minus del W, this is the total work, right, gives du. This is the first law of thermodynamics. Now del Q, it can also be written as du plus del W total, right? And this del W total is nothing but del W dash, and del W loss. This is the sum of all these three words. It is represented as del W total. Okay. So you can simply write it down in such a format that del Q is equals to du plus del W plus del W dash plus del W loss. Okay. So considering this particular system, we are taking that the loss in the friction, loss by the frictional forces are zero. Okay. So we can neglect this particular work term, and we will be obtaining the expression in form of del W and del W dash only, right? Where del W is the mechanical work, which we have already calculated as the value will be equal to PdV. And as per del Q is basically del Q by T gives ds. Okay, this expression for change in entropy will be coming up when we will be dealing with the second law of thermodynamics. Okay, this is basically the main equation that is required as per the second law of thermodynamics. I'll be discussing more about this equation, that how we have come up with this and how we have derived it. Okay, when we will be studying in the second law of thermodynamics. So you have to understand that del Q by T is nothing but equal to ds. Okay, so using these two expressions, we can put these expressions in this particular equation, and we can derive the value of del W dash, right? So it is nothing but TdS is equal to du plus PdV plus del W dash, right? I hope it is clear to everyone. So you can write del W dash as TdS minus du minus PdV. Clear? I hope there is no confusion. I have just put up the expressions that we already know. We have already come up with these equations. Okay, and as per the change in entropy part, we will be dealing in the second law of thermodynamics, where I will be explaining more about it. So first of all, you have to know that TdS basically gives you the change in heat energy. Okay, so del W dash can be represented by TdS minus du minus PdV. Okay, now this expression can also be written as TdS minus du plus PV, differential of u plus PV. Okay, I hope there is no confusion how I have written this. In the last class, okay, someone has asked me some question. EdV not equal to dW dash. No, Ashutosh. We have in the very first class when we were discussing about the work calculation part, I clearly stated that PDV is expressed based upon mechanical work only. Okay, yeah, so it is the only the mechanical work can be expressed in this particular equation as PdV. You cannot express the non-mechanical work because it depends upon the non-mechanical forces, and non-mechanical forces are independent of pressure and volumes mainly. Okay, so based upon that, we cannot relate the non-mechanical work based upon PdV. Okay, so that is why what we are going to express in terms of Gibbs free energy directly. Okay. Right. I hope so. You got it. Okay. So del W dash is given by TdS minus du plus PV, which we have already seen. I'm just showing you again over here that du plus PV. If you open this differential term, you will be getting du plus PdV plus VdP, right? du plus pdv plus vdp, and as since we know that the system is taken at constant pressure, so there will be no change in the pressure, and if we can directly represent vdp equal to 0, and so du plus pdv, we can also write as the differential of u plus pv. Okay, that is what I have done. I have just converted this du pdv. I have taken this minus sign outside, and the differential of du and plus pdv, I have written it down as this particular format. Okay, I hope it is clear to everyone. Okay, so what is u plus pv? We have already known this expression u plus pv. What is u plus pv represents? Exactly. Yeah. So it is an enthalpy value. Okay. U plus PV gives the change in enthalpy. So you can write del W dash is nothing but TDS minus DH. Right? Yeah. Enthalpy. Very good. Very good. So it's clear to everyone, I hope. All right. So this del W dash can be written as TDS minus DH. Okay. Now what I'm going to do, I'm going to take this differential portion again outside based upon the similar expression that we have calculated over here. Okay. Which we have used in order to get U plus PV. Similarly, del W dash can also be written as, agreed? If you have any confusion, you can directly open this differential term, and you will find that it is giving you the same expression because it is at constant temperature. Okay, since the system is taken at constant temperature, so the part where SDT will be coming, that will be neglected, and you can directly write it down, the TDS minus DH as differential of H minus TS, right? Okay, so what does this expression represent? H minus Ts. Yes, yes, yes. I hope everyone is familiar with these equations like G is equal to H minus Ts, A is equal to U minus Ts, H equals to U plus PV. I hope everyone is familiar with these three, four equations, right? Because these are the basics where we will basic equations that we will be you have to understand, you have to learn these equations, because based upon these expressions we will be deriving the Maxwell relations. Okay, so it is important you note down these expressions, and then we can move ahead. Okay, so basically H minus Ts is nothing but the Gibbs free energy part. Okay, so the change in Gibbs free energy is represented by the total maximum non-mechanical work that is done by the system. Okay, as since the loss part is neglected, so the work done in the mechanical force and the non-mechanical force both will be maximum. So based upon that, we have derived this particular expression where the Gibbs free energy is the maximum non-mechanical work done when the system is taken at constant pressure and constant temperature, right? I hope it is clear to everyone. Please note this down. Do let me know if you have any doubt or you want any particular portion to be repeated again. Just learning down the definition that how this has come or how something is coming up to a particular expression, this will not be for a very long time. Okay, so you have to know that how it is being derived, how it is means generated, in order to recall it for a longer period. Okay, so please note this down. And these are such things that you will be doing only once in your life. Okay, mainly you will be having a clear indication, yeah, that the change in Gibbs free energy for a particular system at constant temperature and pressure is the maximum non-mechanical work. Okay, you will be going to with this particular means definition directly. Okay, so this is how it is being derived. So please note this down. And then we will be dealing with the Helmholtz free energy. Okay. Okay, Aditya has asked me a question. Sign indicate. What does this negative sign indicate? Okay, the negative sign for DG, I believe, right? This negative sign, right? Right, Adit? Okay, okay. So what happens? Let me tell you. A system becomes stable when there is a change in Gibbs free energy, and whenever this Gibbs free energy gets lower, the system is more and more stable. Okay, because when the Gibbs free energy lowers down, the lesser amount of work will be done in the non-mechanical form, and more will be generated based upon the mechanical work done. Okay, basic thing that you have to note or understand that the system becomes stable. Sorry, the system becomes stable when there is lowering of Gibbs free energy. I hope everyone has come up with this particular expression that delta G is G2 minus G1, right? Everyone has once seen this particular expression that the difference in the Gibbs free energy is given by the Gibbs free energy of state 2 minus the Gibbs free energy of the state 1. That is the final minus initial state. Okay, where the system is stable only if this value is lesser than 0. Okay, whenever G2 minus G1 is less than 0, the system is stable. Okay, whenever this G2 minus G1 is greater than 0, sorry, sorry, I have taken it the wrong expression. Just a moment. Okay, so whenever the difference in free energy is lesser than 0, then the system is said to be stable. Okay, suppose I can give you an example. Suppose there is a system, say at state A, which has more energy. Okay, the system becomes stable when it segregates, when the all the energy is present in the system is taken out of the system, right? So definitely based upon the energy curve, this system will be stable when lower amount of energy is present inside. Okay, so if this is for this particular system, if this is state 1 and this state 2. Okay, and based upon the energy curve, this here is basically the energy. A system goes from state 1 to state 2 only if there is a lowering of energy inside the system. Okay, so based upon this, if you can directly calculate, for this particular state you will be obtaining a Gibbs free energy as G1, and for this particular state you will be obtaining the Gibbs free energy as G2. Okay, so delta G, as we know, is a state function, and it is represented by G2 minus G1, right? So this is what I hope everyone has come up with this expression in their BTech terms, because it is very common for the stability of the material to understand its relation with the change in free energy. Okay, so the change in free energy is given by G2 minus G1, and if it is lower than 0, then the system is said to come under the stable condition, and if it is given greater than 0, the system is said to be unstable. Okay, similarly, if G2 minus G1 is equal to 0, then the system is said to be at equilibrium. Okay, so considering this particular three expressions, what we have done, we have already considered a system to be a stable system. Okay, so for this stable system, this delta G will definitely be a negative value, right? This delta G will definitely be a negative value, and this dg or delta G is the same thing, and this negative sign is used to compensate with that negative value, because the mechanical work, this sorry, the non-mechanical work, it can never be in the negative terms, right? So we already use a negative sign in order to compensate it for the stable system. Got it, Adit? I hope it is clear to you now that why we are taking the negative sign over here. Okay. All right. So I hope everyone has noted it down. Okay. All right. So we have already seen it for the Gibbs free energy. Now what I'm going to do, we are going to see what is meant by Helmholtz free energy and how it is related to the maximum non-mechanical work. Okay. So part B is Helmholtz free energy. This Helmholtz free energy is given by A, right? We have already seen this. Okay, so you can note it down. It is the maximum non-mechanical work. I'm writing down the definition. Kindly note. It is the maximum non-mechanical work that can be extracted from a system, that can be extracted from a system at constant temperature and volume. At constant temperature and volume. Okay. So Gibbs free energy was at constant temperature and constant pressure, and Helmholtz free energy is the maximum non-mechanical work that can be extracted from a system at constant temperature and volume. Okay, so note this down. Okay, so similarly, based upon the first law, we are going to derive this relation based upon the first law. We know that del Q minus del W total gives D. That is the change in the internal energy, right? So you can write down del W total will be equal to del Q minus du, right? And this del W total is nothing but the sum of mechanical, non-mechanical, and the so this, if you see that there is a maximum non-mechanical work, I've already told you, if there is no loss inside the system, the loss of work by the system, then there will be only mechanical and non-mechanical work, and both will be having a maximum values. Okay, so you can directly write it down over here, that del W plus del W dash plus del W loss gives del Q minus du. Okay, and we are considering that there is no loss inside the system, so we are taking del W loss to be equal to 0. Okay, so you can directly write down del W dash as del Q minus du minus del W, right? And this is the maximum non-mechanical work, because there is we are neglecting the factor that there is any loss in the work. Okay. All right. So if you consider this equation, we have already seen that del Q is nothing but equal to TdS and del W, that is the mechanical work done, is given by PdV. Okay, so you can directly write it down here as TdS minus du minus PdV, right? I hope everyone is getting this equation. Try solving it on your own. Okay. So what we have to see in that, what we have considered that the particular system is taken at constant temperature and constant volume. Right. We have and since the volume is constant, so we can put the mechanical work done will be equal to zero as the change in volume is zero, right? So we can neglect the mechanical work portion as well. Okay, so del W dash maximum is given by TdS minus du, right? And it can also be written as minus d u minus TA, right? And we have seen this expression u minus Ts is nothing but equal to the Helmholtz free energy that is represented by A. Okay, so del W dash max is nothing but equals to minus dA. Okay, I hope it is clear to everyone how I have taken these conditions. Okay, so what we have considered that there is no loss of work done by the system, and temperature and volume, temperature and volume are constant. Okay, these two assumptions we have taken now in order to obtain the Helmholtz free energy with the maximum non-mechanical work done by the system. Okay, please note those down and do let me know in the chat box when you are done with it. So I hope if someone asks you what is Helmholtz free energy and how it is related to the non-mechanical work, so you can directly state this expression in order to explain them. Okay. So written. Okay. Okay. Very good. All right. So we'll be doing with some numerical based upon these equations that we have derived for work and all. Okay. And then we will be moving on to our next chapter where we will be dealing with different thermodynamical relations. Okay. And Maxwell equations and all. Okay. So it is question number 8, I think. Right. Okay. So note down the question. 1 mole of nitrogen, 1 mole of nitrogen at 273 Kelvin, at 273 Kelvin and at constant 1 atm pressure, and at constant 1 atm pressure has pressure has del Q, means the change in heat, the change in heat equal to 3000 joules and the work done was equal to 832 joules. Okay, so there is a 1 mole of gas of nitrogen gas in the system, which is kept at 273 Kelvin, and there is a constant 1 atm pressure that has been applied over the system, and it has the change in heat equal to 3000 joules, and the work done was equal to 832 joules. Okay, so you have to calculate. The first part is you have to calculate the final states of the gas. Final states of the gas. Okay, and also you have to calculate what will be the change in internal energy and the change in enthalpy. Okay, so please do this based upon all these expressions that we have derived earlier. You can easily solve it. Okay, now I hope you know what is meant by the final state of the gas. A state of a gas is represented by a state of a gas is represented by its values of pressure, volume, and temperature. Is given by pressure, volume, and temperature. Okay. So if you see clearly here, the pressure temperature is given for the initial state. You have to find it for the final state of the gas. Okay. So you have to calculate the pressure, volume, and temperature for the final state of the gas in the first part. And for the second part, you have to calculate what will be the change in internal energy and the change in enthalpy. Okay. Please do. Please try solving it. Okay. Okay, so I can see that only one is student answer. What about others? I hope everyone is trying to solve this question. Done? Okay, look here. I'm solving it. U is 2168G. Yeah, the answer is close. Good, yes. Okay, okay. I'm doing it. 22.4. What is 22.4? Liters, meter cube. Monica, do use the units as well, okay? So I'm just putting up the solution. Okay, those who have not done, please look here, and those who have understood, keep on going with your answers. Okay, try solving it on your own first, and if in case if you have any doubt, you can check it over here. Okay, so we know that the number of moles is given as 1. Okay, and temperature, that is T1, the initial state condition, it is 273 Kelvin. Similarly, the pressure is constant, and the pressure 1 is given as 1 atm. Okay, we don't know about the volume of this particular relation. We means for the present state, we don't know what is the value of volume, that is v1 is not known. Okay, so first of all we have to calculate v1, and then we have to calculate p2, v2 and t2 in order to get the state of the gas. Okay, so we know by the gas law that p1 v1 is equal to nRT1. Okay, so say this is equation 1, and P2 V2 is equal to nRT2. This is equation 2. So based upon this relation, you can say P1 V1 upon T1 is equal to P2 V2 upon T2. Okay, so now in the question you can see that the pressure is taken as constant 1 atm. Okay, so the pressure value P1 is equal to P2, and it is equal to 1 atm. Okay, so it is basically an isobaric process. The pressure remains constant when the system moves from one state to another. Okay, so P1 V1 can be neglected down. You can remove this P1 and P2, and you can directly write the expression as V1 upon V2 is equal to T1 upon T2. Okay, so now you got a general relation between V1 V2 and T1 T2, right? Okay, so now what I'm going to do, I'm just going to calculate what will be the volume for the first state, and then we will be dealing with the second state. Okay, so we know based upon the first means the ideal gas law that P1 V1 equals to nRT1, and here we already know that P1 is nothing but 1 atm, and volume we are calculating V1 is equal to n, that is 1 mole, and R. What is the value of R you have taken? Do let me know in the chat box what the value of R you are taking. 0.0821 exactly, because you see that this particular expression is the expression for pressure is given in the atm for atmospheric pressure, so you have to take it as 0.0821. Okay, and the temperature is already given as 273 Kelvin, right? Yeah, 273. So you can directly calculate the value of V1. What is the value of V1? I'm also doing. Please calculate. It is 22.41 liters. Okay, as it will be giving the value of volume in liters. Okay, so V1 we have calculated now, and based upon this, we will be similarly calculating for the V2 and T2 part, and then we will be using this expression. Okay, so what we know, what we have seen in this particular equation, that the amount of work, that is the change in work, is provided to us. Okay, and we know that it is an isobaric process. Okay, as the pressure remains constant, and we have already derived the expression for work, that is nothing but P V2 minus V1, right? This is the final volume minus initial volume. When we multiply with the pressure, we get the work done by the system from going from the initial state to the final state. Okay, for an isobaric process. Okay, now we know the value of pressure, we know the value of V1. We can directly calculate the value of V2, as we also know the value of work done, right? So try solving this. Okay, so the work is 832 joules. Work done is 832 joules. What is the value of pressure? What I have to take in pressure form? Means at pressure, what I have to write? Should I write 1 or some other value? 1 ATM. No, Dikshita, this is where you are wrong. You have to consider the units. Okay, you are converting, as you see that the work done is given in joules, so you cannot take it into the ATM units. Okay, you have to convert it, the value of pressure, into pascals. Okay, so here you have to write 10 to the power 5 pascals. Okay, it is in pascals. I'm also writing the units as well. Okay, similarly, the final volume is V2 minus V1, that is 22.41 into 10 to the power minus 3 meter cube. Okay, I hope everyone is getting how I have written this down, because basically I hope everyone knows how the unit conversions are there. 1 ATM is equal to 10 to the power 5 pascals, and 1 meter cube is equals to 1000 liters. Okay, and as since the energy is given, the work done is given in joules, so you have to convert it into the SI units of pascals and meter cube. Okay, so what is the value of V2 you are obtaining from here? Please solve it and let me know. Thirty point seven two. Okay, what about others? Others are not giving me answers. I want this answer from Sandeep now. Sandeep, Simon, and Shusavan. I want this answer from you now. What is the value of V2 that you are obtaining? Okay, so Suman has given. Please answer over here. Otherwise, I will ask the faculty, ask the team to remove you from here. Okay, so please answer it. Be active in the class. What about Simon? Simon, are you listening me? Okay. So I hope you are solving this now. 30.72. Very good. Okay. So all of them are active then. Okay. So V2 I have taken as 30.72 liters. Okay. So this is how you will be obtaining the value of V2. We already know the value of V1, and we all it is already given in the question that T1 is 273 Kelvin. Okay. So based upon this, you can directly calculate the value of T2. Okay. So use this expression. No, it is not. It is, you can say that it is in meter cube. No, actually, it is not in meter cube. It will be in liters, Anuj. This 30.72 will be in liters, right? All right. So based upon the earlier expression, that is V1 upon V2 gives T1 upon T2, you can directly calculate the value of T2, which will be equal to 273 into V2, that is 30.72, divided by 22.41. Yeah, volume change will be in meter cube that you will be obtaining for this particular expression. Okay, you will be obtaining the value in meter cube only. Okay, then you are converting it down in order to get the value in liters. Okay, and 30.72 I believe is the answer for the liters part, right? I've not calculated this, but based upon your friends who have told me the answer, 30.72 is in liters, right? Yes, exactly. So we have converted it from meter cube to liters so that our calculation for other expressions, like over here we have to convert. If it was taken in meter cube, then you have to convert 22.41, and there will be an additional 10 to the power minus 3 terms included in every expression wherever the volume is used. Okay. So to remove that, we have just converted into liters and we have used it over here. So T2, what is the temperature? 374 Kelvin. Very good. Right. So we have obtained the state of the system, that is P2 equals to 1 atm, V2 is equals to 30.72 liters, and T2 equals to 374 Kelvin. Okay. Done with on the part first. I hope it is clear how we have derived this particular expressions and how we have calculated the final state of the system. Okay. All right. So for the second part is quite easy actually. We have to calculate what will be the change in internal energy and what will be the change in enthalpy. Okay. All right. So if you have calculated the first part, then you can easily calculate this based on the upon the expressions that we have derived earlier. 2168 joules. Okay. And what about delta H? Delta H is equal to Q. Exactly. Exactly. Right. Right, very good. As you can see that delta U, you can directly calculate based upon the first law, that is del Q minus del W. And del Q, I believe, is 3000 joules. And del W is given by 832 joules, which I believe will come to 2168 joules. Right? Similarly, as per the system is taken as iso isobaric, right? The system is an isobaric process, that is at constant pressure. And for constant pressure, del Q is nothing but equal to delta H, right? So it will be equal to 3000 joules, right? Exactly. So it was a simple question. Similar questions are being asked. So I hope there will be no doubt in this. We'll be practicing some more questions in the assignments and test portions when I will be giving you them. Okay. So please remember the means the general expressions. Okay. You can directly calculate all these values based upon the general expression. Okay. So you have to remember the general expression first of all. All right. Okay, so write down another question. Question number 9. It is just the continuation of the first question that we have done. Find the values of Cp and Cv. Find the values of Cp and Cv and gamma also. Okay, for nitrogen from the given data, from the above data. For nitrogen from the above data. Above question is done, right? Okay, it is quite simple. We have already generated the expression for their relation in our last class. Use them and you will be directly getting the value of Cp, Cv and gamma. Okay, done. It is very simple. We have already calculated the expressions. Okay, Dikshita and Yash has given me the answer. Cp is 31.57, Cb 2.82, gamma 1.38. Okay. Why is everyone getting different values? Though they are getting the same ratios. You should be getting the same value, right? Okay, I'm solving it out. Okay, I'm solving it. Please see. Okay, so we have already calculated that the change in internal energy, that is delta U, is already calculated as, what is the value of delta U? 2168 joules, right? So delta U was given as 2168 joules. And we know, based upon the expression relation between internal energy and CV, that delta U is nothing but NCV dt, right? Now the system is given at 1 moles, that is there are only 1 moles. CV we have to calculate, and dt will be final initial temperature, that was 273 Kelvin, right? So this value will be nothing but equal to 100 Kelvin. Okay, so you can directly calculate 2168 by 100 will give you the value of CV, that is equal to 21.68, right? So why are 31.57 joules per mole Kelvin? Okay, you have to see over here that this is 21.68 per joule per mole Kelvin. Okay, it is very simple. You just have to put up the change in internal energy in the expression for the CV. You will directly get the change in means you will directly get the value of CV. Okay. Similarly, this is for CP. Similarly, we have also obtained that the change in enthalpy was 3000 joules, right? And we know that delta H is nothing but NCP dt, right? Now again, dt is given by 100 Kelvin. That is the change, the difference in temperature, 373 minus 273 of the two states. The Cp that we have to calculate, and number of mole is given by 1. Okay. Temperature is 374 Kelvin. Okay, that won't be still won't be affecting anyone. Whether you take the difference to be 100 or 101 Kelvin, it won't be affecting anyone very much. Okay. Anyway, so the closed answers are okay. I'm not discussing about them, but there is a wide variations in the answer. I was discussing about those answers. Anyways, please see over here that delta H is given by 3000 joules, which is equal to Cp by 100. Okay, so you can directly write Cp as 30 joules per mole Kelvin. Okay, if you take 101, it will come something around 29.997 something. Okay, so that will be also a correct answer. No issues in that. Okay. Similarly, you can calculate it for gamma. That is the heat factor ratio. That is gamma is given by Cp by Cv. Okay, so it is 30 by 21.68, and the ratio will be approximately equal to 1.38, right? I hope everyone is getting the point how I've calculated this. All right, please note this down, and then we will be moving to our next chapter. With this, we officially calculate our chapter number 4, that is the heat energy part. And now we will be going to the new chapter where we will be discussing about various thermodynamic relations. Okay. And we will be deriving the auxiliary relations and the Maxwell relations and all. Okay. And mostly the questions are directly based upon this relation. So you have to understand, and then I will be giving you a short trick how to learn about these Maxwell equations, so that you don't have to go up with your complete procedure of calculating or deriving the Maxwell equation in the examination. Okay, so it will be quite simple and easy to understand. All right, so done everyone. Shall we move ahead? Okay, very good. Okay, so this is chapter number 5, thermodynamic relations. Okay, so chapter number 5, thermodynamic relations. These are basically also known as auxiliary relations. They are also known as auxiliary relations or Maxwell relations. Okay, so they are also known as auxiliary relations or Maxwell relations. Now, what thermodynamic relations basically relate is that they relate the enthalpy, internal energy, gives free energy, and Helmholtz free energy in terms of the various fundamental properties like pressure, volume, temperature, and these relations, these relations, enthalpy, internal energy, gives free energy, and Helmholtz free energy in terms of various fundamental variables. So, fundamental variables that are pressure, volume, temperature, and entropy. Okay, so they basically gives a relationship between enthalpy, internal energy, gives free energy, and Helmholtz free energy based upon various fundamental variables and entropy. Okay, so before understanding these relations, you have to be very clear that you have to learn these particular expressions related to H, that is U plus PV, G, that is equals to H minus Ts, and A, that is equal to U expressions, fundamental expressions. The complete expression relations that we will be deriving will be based upon these three expressions only. And along with this, there will be first law of thermodynamics, definitely. Okay. So these are the fundamental expressions. Okay. All right. So in the very first part, we will be deriving the thermodynamic relations based upon the differential form. Okay. Fundamental means, sorry, thermodynamic relations in differential form. All these questions are direct questions which are mainly asked. Okay, so you can take a look in the previous year's questions and you will find such questions. Okay, anyways, so based upon the differential form, we already know that the first law of thermodynamics says that first law states that du is given by del q minus del w, right? Du is given by del q minus del w, and we have already derived that del q is nothing but equals to tds, and del w is nothing but equals to pdv. Okay, so this is the differential form of internal energy relation with the thermodynamic variable. Okay, so this is equation number one. You can directly write it down. The derivation is not at all difficult. Okay, you just have to understand that what particular terms means and how they are being expressed in the other terminologies. Okay, so du is nothing but equal to tds minus pdv, and this is your first relation. Okay, similarly, we know that h is given by u plus pv, right? Now, what we are going to do, we are just going to differentiate this whole terms. Okay, we are going to differentiate this complete expression. Okay, so it will be nothing but dh is equal to du plus pdv plus vdp, right? Now, we have already calculated the value of du from the above equation. You can replace it with the help of the first equation. It will come dh is nothing but tds minus pdv plus pdv plus vdp, right? So this minus pdv and plus pdv will be cancelling out each other, and dh is given by tds plus vdp. This is expression number 2 in the differential format. Clear? Please note this down and then we will move ahead. Clear? I hope there is no confusion that how I am deriving all these expressions. Okay? Because you have to understand these four expressions that we are going to generate right now, because Maxwell equations are being derived based upon these four expressions only. Okay? All right. Very good. So then calculating for the Gibbs free energy part, we already know that G is given by H minus Ts, right? So we will be just differentiating the complete expression, and it will give dG is equals to dH minus TdS minus SdT, right? Please try solving out in your own method, okay? Because if there are some mistake, if some way I do, okay, so you are not doing the same mistake, and you can clarify me also. Okay, so G is given by H minus Ts, which is nothing but dG is, we are going to differentiate them, and we will be obtaining the expression as dG equal to dH minus TdS minus SdT. Okay, so dH we have already calculated from the expression number 2, and we will be obtaining the value as TdS plus VdP minus TdS minus SdT. Okay, so this plus TdS and minus TdS will cancel out, and dG is nothing but equal to VdP minus SdT. Okay, and this is expression number 3. All right. Similarly, for the Helmholtz free energy, A is given by U minus Ts, right? So differentiate the complete equation and put up the values, you will be obtaining the relation. Okay. So dA is nothing but du minus Tds minus SDT, right? So put up the value of du that you have obtained earlier. This in equation number 1, the value of du we obtained as Tds minus Pdv. We'll be putting this value in order to calculate the auxiliary friction. Okay, so it was Tds minus Pdv minus Tds minus SDT, and this is equals to dA. So you can again cancel this Tds term, and you will be getting the expression as dA equals to minus Pdv minus SDT. Okay, and this is expression number 4, right? Please note this down. This is basically the thermodynamic relations that is being expressed in the differential form. Okay, so please note this down and then we'll move ahead. I hope there is no confusion how I have derived all these expressions. In case if you have any doubt, do let me know in the chat box. Okay, done. Very good. Okay, so these are the expressions in terms of the differential format. Okay. Now what we are going to do, we are going to see the thermodynamic relations in the auxiliary form. Okay. So this is the second part of our section, or the second section of our chapter, that is thermodynamic relations in auxiliary form. Okay. All right. So if you consider that a particular expression, say a particular function is given z, which consists of two independent terms x and y, then the differentiation of z will give you how you can differentiate z. I'm just differentiating z over here. This differentiation of z will be represented by del z by del x at constant y dx plus del z by del y at constant x dy, right? So if a function is given which contains two independent variables, then the differentiation of this particular function is given by differentiating the whole function with in terms of x, keeping y constant with it dx term, plus the differentiating the complete function with y, keeping x as constant with the dy term. Okay, I hope you know this, how to differentiate the more than one independent variables, how when they are present, how to differentiate a particular function. Okay, so this is what you will be obtaining. All right, so we have already seen in our last to last class, that if this particular thing is present, like if this particular section for a function, if such function is given like z is equal to fx comma y, for such function to be a state function, what was the relation? Del square z, the double differentiation of z in terms of x and y, should be equal to del square z in terms of y and x, right? A function is said to be a state function when its double differentiation taking x first and y second is equal to its double differentiation taking y first and x second. Okay, so we have already seen this relation. Okay, so what I'm going to do, I'm just going to write it in the auxiliary form. Okay, so you can directly write this dz as mdx plus ndy. Okay, and m here is nothing but del z by del x, and n is given by del z by del y. Right, you can write it in this term. Similarly, this is for the state function. If a function is a state function, this is the necessary condition that the system should follow. Okay, so what I'm going to do, I'm just going to use this state function, the necessary condition for the state function, and will be relating in terms of m and n. Okay, so a function will be state function when del m by del y is equal to del n by del x. Right, I can write it like this because m is already the differential of the function z in terms of x, and n is already the differential of the function z in terms of y. So we can directly differentiate it once with the terms of x and y respectively in their order, and we can directly get when the system is a state function if this particular expression holds. Right, please note this down, and then we will be moving it. Okay, so based upon this, this is basically the auxiliary relation that is being shown here. Okay, and what we will be doing, we will be using the expressions that we have obtained earlier. Okay, the four expressions that we have obtained earlier, 1, 2, 3, 4. We will be using them, we will be converting them in the auxiliary form, and we will be deriving the values based upon them. Okay, so from the first expression, that was for du, right? Internal energy was given by TdS minus PdV. Okay, so from this expression, the du can also be written as del u by del s at constant volume ds plus del u by del v at constant entropy dv. Right, we can write this expression like this. Right, what I am doing, we have obtained this equation, this expression, and we are converting them in the auxiliary form like this. Right, so we can write the equation 1, that is du, in terms of del u by del s at constant volume ds plus del u by del v at constant entropy dv. Right, so with this you will see that del u by del s at constant volume is nothing but temperature. Okay, and similarly del u by del v at constant entropy is given by minus pressure. Right, this is the auxiliary form. Please note this down. I hope it is clear that how we are deriving all these expressions. Similarly, for the second equation, it was given by the enthalpy part, that is dH is equals to TdS plus VdP. Okay, So similarly, we can also write dH as del H by del S at constant pressure ds, right? Plus del H by del P at constant entropy dT, right? So we can say that del H by del S is nothing but equal to temperature, and del H by del P at constant entropy is nothing but equal to volume. Okay, this is at constant pressure, right? Similarly, for the third part, that is for the free energy, you can also write at the equation that we obtained was dg is equal to vdp minus sdt, right? So you can write the dg term as del g by del p at constant temperature dp plus del g by del t at constant pressure dt, right? So it means that del G by del P is nothing but equals to volume, and del G by del T is nothing but equals to minus entropy. Okay. Similarly, for the fourth expression, that is for the Helmholtz reaction part, it is dA is equal to minus SDT minus PdV. Okay. So you can also write this dA as del A upon del T at constant volume dt plus del A upon del V at constant temperature dV, right? So del A by del T is nothing but equals to minus entropy, and del A by del V is nothing but equals to minus P. Okay, I have left out these terms over here. The constant term is temperature and the constant is pressure over here. Similarly, for this equation, the constant is volume and temperature. Okay. All right. Please note this down. This is basically the thermodynamic relation in the auxiliary form. Okay. Note this and let me know in the chat box when you are done with it. Okay, very good. All right. So I'm just summarizing the auxiliary form in a tabular format so that it is easy for you to revise. Okay. So I'm just summarizing the auxiliary form. Uh, you obtain temperature by del H by del S at constant pressure, and also by del U by del S at constant volume. Okay. This is your first. And second, you obtain your pressure by minus del U by del V at constant entropy, and also by minus del A by del V at constant temperature. Okay. Similarly, for the third part, that is for volume, del H by del P at constant entropy, and also you obtain volume by del G by del P at constant temperature. Okay. Similarly, for the fourth part, S is given by, that is entropy is given by minus del G by del T at constant pressure and minus del A by del T at constant volume. Okay. So this is the auxiliary form, and mainly the question are asked from the auxiliary form in the match the following format. So you can directly write out down the values based upon this. Okay. All right, put it inside a box so that you can easily check and revise it regularly. Okay. All right, so we have seen the thermodynamic relations in the differential form. Then we have also seen the relations in the auxiliary form. Now what we are going to do, we are going to find the Maxwell relations. Okay. So the third section of this chapter is the Maxwell relations. Okay. So as we have already seen the four equations that we have derived in the differential form, I'm just writing it over here again. So the first expression was du is equals to TdS minus PdV, and similarly for enthalpy it was dH, which is equals to TdS plus PdV. Similarly for Gibbs free energy dG, it is equals to VdP minus SdT. Make sure you remember these four equations. You have to remember these four equations. You make some notations or some of your concept so that you don't get confused in these four equations. You have to learn these equations in order to get calculate the Maxwell relations. Okay. So dA is nothing but minus PdV minus SdT. Right. These four equations are very important. Every year one question is definitely being asked from the Maxwell relation. So, and Maxwell relations, in order to derive them, you have to understand these four equations. Okay. So please learn them. Okay. All right. So we have already seen that when the function z was a function of two independent variables, so then the differential form we can write it down as mdx plus ndy. Right. So if you see all these four equations, you will find that they are quite related to this particular differential form. Right? They are related to this differential form of z. You can directly relate it with these four equations. Okay. So from the first equation, okay, I'm so many times using the same notation. Okay, so from the first equation, you find that du is equals to TdS minus PdV, where T is nothing but can be replaced by M, and ds is nothing but dx. Similarly, P is nothing but replaced by N, and dv is nothing but dy. Right? And this is the dz function. Agreed, everyone? So what Maxwell relation says, Maxwell relation is nothing but the representation of the state functions. Okay, because you see that u is basically a state function. So you have to means satisfy this equation that del m by del y should be equal to del n by del x. Okay, a function to be a state function, this particular expression should definitely hold true. Okay, and we know that internal energy is a state function, so this expression will definitely hold true, and we can write it down as m. What is m? M is nothing but t. So del t by what is y? Y is given by your dv function, so del y, sorry, del v is equal to, del v is equals to del m, that is nothing but del p by del x, that is nothing but del s. Okay, and this is given by this equation is given by at constant entropy, and this relation is given at constant volume. Okay, so this is nothing but the Maxwell relation for the first case in terms of internal energy. I hope it is clear how I have derived this particular expression. Clear now? Do let me know in the chat box if you want me to repeat again. I will repeat it. This is how you basically derive these Maxwell relations based upon the four equations that you have calculated in the differential form. Okay. So similarly, try deriving all these expressions, the Maxwell relation, directly from these equations that are being given here. Okay, on your own. Try solving it on your own first, and then I will give you a hint how to learn them. Okay, so that you don't get confused or forget about the relations. Okay, I did a mistake over here. It will be not del p by del s, but it will be minus del p by del s. Sorry, I'm just writing it again. Don't make any such mistakes. Okay, so this will be minus del p by del s at constant volume, because n is not p, n is minus p. Okay, on relating this with this expression, you find that it is positive term here, so you have to consider minus p as the total n value. Okay, so similarly derive it for the remaining three equations, and then I will tell you the trick. Okay, I've written a wrong equation over there. No one is seeing this. How come, yeah? It will be VDP. DH is given by TDS plus VDP. Okay. All right. So DH is given by TDS plus VDP. Okay. For DG also, I have written wrong equation DG. VDP minus SDT for DG. What I have written wrong in DG? I think DG is correct, right? VDP minus SDT. Yeah, we have derived the same equation VDP minus SDT. Okay, okay. Anyways, del T by del P at constant entropy equals to del V by del S at constant pressure. Okay. So based upon the third equation, that is dG VdP minus SdT, then also write it down as del S by del P at constant temperature is equals to minus del V by del P del T at constant pressure. And finally, for the Helmholtz free energy, that is dA, can directly write it down, which is equal to minus SdT minus PdV, where del S by del V at constant temperature is equals to del P by del T at constant volume. Okay? I hope everyone has written all these four Maxwell relations. Right? Okay. Okay. Very good. All right. So verify your answer once. That is with the answers that I have written. Because if ever any of this particular term is missing, if you write it wrongly, then you will be getting a wrong expression. Okay. So please make sure you check all these four relations with the how I have written it down. Okay. All right. So questions are mainly asked from the Maxwell relation, that how you have to calculate this, means how you have to, they will give you different relations. Okay. And they will tell you it is equal to which particular relation. Okay. There will be some, there will be only one correct answer, and mainly they will give you wrong answers in that. And you have to, instead of deriving how you have to get the exact answer in the first go, that is what I'm going to give you in the short trick over here. Okay. So make sure you remember that. Okay. So first of all, what you have to see in this particular relation, that all these four Maxwell relations that we have developed, they contain only four terms: T, P, S, and V. All these four relations are based upon these four terminologies, that is the fundamental relations, fundamental variables of pressure, temperature, and volume, and entropy. Okay. The complete Maxwell relation is based upon these four terms. Okay. Secondly, what you have to do, you have to remember this one particular expression, del P by del T del S by del V. Okay, it is at constant volume and this is at constant temperature. You have to make sure that you remember this particular expression, because it is quite important, as this particular equation is also known as Clausius-Clapeyron equation. Okay, and we will be deriving different volume and temperature terms, but we will be reading with the unary phases. Okay, then we will be using this Clausius-Clapeyron equation there. Okay, so what you have to do, you just have to remember this particular equation, that is the Clausius-Clapeyron equation, and this is given by TPSV, or you can make your own way. Okay, so you can directly remember this particular equation, and then you can find out the other equations of the Maxwell directly based upon this. Okay, so make sure you have to remember this. And for generating the other Maxwell relation, it is nothing but very simple. First of all, the Maxwell, this is one of the relation, one of the four relation that we have obtained in the above Maxwell equations, right? So this is one of the four equations that we obtain in the above relation. In order to obtain the second, third, and fourth, what we are going to do, we are just going to reciprocal these terms, and you will be obtaining another relation. Like, okay, so if you see that del T by del P is equal to del V by del S, and this at constant entropy, and this is at constant pressure. This is a second Maxwell relation, and what we did, we just reciprocal the Clausius-Clapeyron equation. Okay, we just reciprocal. We have taken del T. This change in pressure will be at the denominator, and you will be obtaining the second relation of the Maxwell. Clear? We are just going to take this del T part over here, and we will be exchanging it with the del S part over here. Okay, so we are going to put del T over here, and del S will be we will put over here. Okay, so the third relation you can directly obtain by del P by del S is equal to del T by del V, and this is at constant volume, and this is at constant entropy. Okay, so this is a third relation, and one thing that you have to note over here, that whenever it is in del P by del S or del S by del P form, it will be indicated with a negative sign. Okay, so this is the third relation, and how we derive? We derive based upon exchange del T and del S. And the second thing that you have to remember here, whenever pressure and entropy are together, pressure and entropy, that is P and S, are together, you have to put a negative sign. Okay. Similarly, for the fourth Maxwell relation, you just have to do the reciprocal of the third part, third relation that we obtained, and you will be getting the fourth one. Okay. So simple enough, del S by del P is equals to del V by del T. And it will be at constant temperature, and it will be at constant pressure. And this negative sign will definitely be there. Okay. So this is the fourth relation. Reciprocal of third relation, right? So you just have to learn this Clausius-Clapeyron equation. You have to learn it because there is no other choice. We will be solving many numericals based upon Clausius-Clapeyron equation. So you have to get the idea. So you just have to learn this Clausius-Clapeyron equation, and based upon that, you first reciprocal it down, and then you replace it with the del S and del T together, and you will be obtaining the third and fourth relation as well. Okay, so you can directly understand you can directly produce, instead of going through all the derivation, writing out the dh du and the differential equation and then deriving the relation in Maxwell form. You can directly go through these equations and you can directly learn them. Okay, you can directly produce the other three based upon the first Clausius-Clapeyron equation. Okay, so I hope it is clear to everyone. In case you have any doubt, please turn back your pages and let me know in the chat box. Okay. If you want me to repeat any particular point again, do let me know then. Clear? Okay. All right. So with this, we will be ending our class. Okay. If you have any doubt, you can ask me now. And yeah, as Gayatri was asking me about various examples of the specific property, Gayatri, are you there? So she is not there then. Okay. Okay. Very good. Okay, so you were asking me about some examples of the specific properties, right? So some common examples, I'm just writing it down. Please note it. Examples of specific properties. These are some of the most common ones. Mainly the question is not directly asked to give the examples of the specific properties, but you should have some ideas, examples of the specific properties. So, density. Density is one of the most common example. Okay, then specific heat capacity, definitely. Specific modulus, or specific Young's modulus, you can say. Specific Young's modulus. These three are the most common one. Along with this, you can also write a specific gravity and a specific volume. Okay, so these are some common examples of specific properties. Please note this down, and if you have any questions, then do let me know in the chat box, or else we will close the session for today. All right. Thank you, everyone.
KP classes dedicated to excellence.